In this video, I am going to explain spinels, which I have taken from the coordination chemistry. Before going to this topic, you should know what is crystal lattice, what are tetrahedral void, and what are octahedral void, and so on. Spinels, these are basically a type of crystal solids which have the general formula that is AB2X4. This is the general formula of spinels. X can be anything like oxide, sulfide, fluoride, selenide, etc. A is nothing but divalent cation and B is trivalent cation. If divalent cation goes into tetrahedral void and trivalent cation if goes into octahedral void, the spinel formed here is known as normal spinels. This is the combination of normal spinel. Second one, if divalent cation goes into octahedral void and try both the things, half of the tetrahedral void and here half of the octahedral void. This is the combination of inverse spinel. The next question arises, that will be how to identify this. The best way, that is crystal field stabilization energy. Before explaining that, let me give the tips and tricks that will be more useful for your exam. Tips and tricks. The first point, both divalent cation and trivalent cations are non-transition element. The spinel formed here is known as normal spinel. If both divalent and trivalent are non-transition metal, the spinel over here is known as normal spinels. Second point, divalent cations is non-transition metal and trivalent cation is transition transition metal with these electronic configuration D1, D2, D3, D4, D5 is not there, D6, D7, D8 and D9. With this electronic configuration, the spinal over here is known as normal spinal. Third one, divalent cation is transition metals with this electronic configuration, that is D1, D2, D3, D4, D6, D7, D8, D9 and trivalent cation is also transition metal with this electronic configuration 0, D5, D10. The spinal formed here is known as inverse spinal. Inverse spinal. And last point is D3 and D8 configuration has highest crystal field stabilization energy. They prefer octahedral void. Fourth point, D3 and D8 configuration has highest crystal field stabilization energy. Highest crystal field stabilization energy. I have given tips and tricks, so it will be very easy for you to identify whether it is normal spinal or inverse spinal. General formula of spinal, that is AB2X4. X may be anything like oxide, sulfide, fluoride, selenide and etc. Therefore, here I am going to take the first example, that is MgAl2O4. Here we can write MgAl2O4. Here this I am going to write Mg plus 2 divalent cation, and here the next I am going to write the trivalent cation Al plus 3. I have given the tips and tricks. According to that tips, we know that if divalent and trivalent are non-transition metal, very clearly we can write that is an example for the normal spinal. The next example I am going to write FeCr2O4. Here we can write FeCr2O4. Therefore, here I am going to write the divalent cation, that is Fe plus 2. Here I am going to write the trivalent cation, that is Cr plus 3. Here Fe plus 2. We know that this is D6 configuration. Cr plus 3. This is D3 configuration. We know that D3 and DH configuration has highest crystal field stabilization energy and they prefer octahedral void. Highest crystal field stabilization energy. Therefore, here crystal field stabilization energy of Cr plus 3 greater than crystal field stabilization energy of Fe plus 2. Therefore, we know that this is an example for the normal spinal, or we can say tripositive is greater than dipositive. So clearly understood, this is an example for the normal spinal. Crystal field stabilization energy is the best way to identify whether it is normal spinal or inverse spinal. There is two things which have to be remembered. First one and second one. Here, crystal field stabilization energy of tripositive ion is greater than crystal field stabilization energy of dipositive ion, means in octahedral field, means we can say spinal over here is known as the normal spinal. Second one, this is very simple. You just have to remember one, other is reverse of that. In the case of second one, here crystal field stabilization energy of dipositive ion is greater than crystal field stabilization energy of tripositive ion. Therefore, here the spinal over here is known as inverse spinal. In the case of FeCr2O4, crystal field stabilization energy of tripositive is greater than crystal field stabilization energy of dipositive. Therefore, this is an example for the normal spinal. Next example, that is Fe3O4. The general formula of the spinal, that is AB2X4. X can be anything like oxide, sulfide, fluoride, selenide, etc. Fe3O4, it does not look like that. You can convert into that general formula. Therefore, here I am going to convert this Fe2O4. Here Fe, we can say, here I am going to write Fe, that is in the plus 2 oxidation state. Here I am going to write Fe, that is in the plus 3 oxidation state. Here Fe plus 2, this is D6 configuration, and Fe plus 3, that is D5 configuration. Here, in the case of D5 configuration, the crystal field stabilization energy, that is 0. CFSE is 0 here. Now I am going to calculate the CFSE, crystal field stabilization energy of D6 configuration. Here, D6 configuration, e.g. 1, 2, 3, T2G, here 6, 1, 2, 3, 4, 5. The sixth one I am going to write it over here. Okay, then here now I am going to calculate the crystal field stabilization energy. Here X into minus 0.4 plus Y into 0.6 plus ZP. Here X is the number of electrons in the T2G orbital. Therefore X we can write that is 4. Y number of electrons in the EG orbital. Y is 2. Then next we have to find out the Z, right? Therefore here one electron pair in the spherical field. Here one electron pair in the spherical field. Then here also 1 in octahedral environment. Therefore here 1 minus 1 is equal to 0. Now I am going to substitute. Therefore here X, that is 4. Instead of X you can write 4 minus 0.4 plus 2 into 0.6 plus 0 P. Here answer it will be minus 0.4. Here no need to worry about this negative charge. Actually this is the modulus of this value. Therefore here answer is 0.4. Therefore here crystal field stabilization energy here Fe plus 2 CFSE is greater than Fe plus 3. CFSE. Crystal field stabilization energy of Fe plus 2, that is greater than Fe plus 3. Therefore, this is an example for the inverse spinel. Next I am going to explain about the mixed spinel. Here I am going to take Mn Fe2O4. Mn Fe2O4. Here Mn, that is in the plus 2 oxidation state. This is D5 configuration, and here the crystal field stabilization energy, that is equal to 0. Next, that is Fe, that is in the plus 3 oxidation state. Here this is D5 configuration. Here the crystal field stabilization energy, that is equal to 0. Both of them are D5 configuration. Crystal field stabilization energy of both of them is 0. You cannot compare based upon the crystal field stabilization energy, and the size is also quite similar. In that case you cannot decide whether it is normal or inverse spinel. Overall it is called mixed spinel. Some of the part remain as normal spinel and some of the portion of the crystal remain as inverse spinel. So overall it is known as the mixed spinel. Not only this, MgFe2O4 also an example for the mixed spinel. here I have given the tips and tricks. Already I have explained, so I am skipping this table. Thank you.